Now we discuss time reversal. Consider a classical mechanical system with a single particle and having a Hamiltonian which satisfies the following condition, that is HQP equal to HQ minus P, where Q is the position coordinate and P is the momentum coordinate. Now if the Hamiltonian HQP is equal to HQ minus P, then the Hamilton's equation remains the same under the mapping Q goes to Q and P goes to minus P with time going to minus T. In quantum mechanics, we consider a similar transformation. We consider a change of the time parameter from T to minus T and consider a mapping in the Hilbert space denoted by theta, such that under this mapping the operator R goes to R and the momentum operator goes to minus of P. So theta R theta inverse is equal to R and theta P theta inverse equal to minus P. And we investigate the properties of the system under these transformation. So the time parameter goes to minus T and the position operator remains the same and the momentum operator changes its sign, and this is identical to the classical transformation that we have considered earlier under time reversal. That's why this is called the time reversal transformation. Now consider the commutator of position with momentum. In quantum mechanics we have xi commutator with pj, where xi and pj are the Cartesian components of the position and momentum operators, is equal to ih bar times delta ij. Now if time reversal is a symmetry operation, we expect this commutation relation to be preserved under the transformation specified by equation 13.2, the time reversal transformation. Let us apply this transformation to this commutation relation. So we get theta, then commutator of xi pj, then theta inverse, and that should be equal to theta ih bar delta ij theta inverse. Now we consider the left hand side and we can expand this commutator. Xi pj commutator is xi pj minus pj xi, and then the application of these operators will give theta xi pj theta inverse minus theta pj xi theta inverse. Now considering the first term, between xi and pj we can insert an identity operator, and theta inverse theta is the identity operator, and therefore we can write this as theta xi theta inverse then theta pj theta inverse. So this is the transformed position coordinate, that is theta xi theta inverse is the transformed position coordinate, and under time reversal transformation, and this remains unchanged. So this is equal to xi, but the momentum operator changes its sign. Therefore theta pj theta inverse is minus pj. And similarly in the second term. We see that under the action of this time reversal transformation, this commutator, the left hand side of this commutator relation have picked up an additional sign, and that's because P, the momentum operators P, picks up an additional negative sign under this transformation. So LHS is equal to minus IH bar delta IJ. But then right hand side is given by this theta IH bar delta IJ theta inverse, and that should be equal to the left hand side, which is equal to minus IH bar delta IJ. Putting these two together we get theta IH bar delta IJ theta inverse is equal to minus IH bar delta IJ. Now if theta was a unitary operator, then theta IH bar delta IJ would be IH bar delta ij theta, that is if theta was unitary, then theta IH bar delta ij would be IH bar delta ij theta. Then this theta will get transported to the position after the delta ij, the Kronecker delta. Then theta times theta inverse would be the identity operator, and we will get IH bar delta ij. But the right hand side is not IH bar delta ij. It has an additional negative sign, and therefore theta cannot be a unitary operator. Now the other candidate for a symmetry transformation is theta being an anti-unitary operator. Now if theta is an anti-unitary operator, then theta IH bar is simply minus IH bar theta, and delta ij is real, and therefore this theta can be taken to the right side. So you will get minus IH bar delta ij theta. Then theta inverse is identity, and we will get minus IH bar delta ij, which is exactly same as the right hand side. So this condition that the commutators remain unchanged under this transformation necessitates that theta is an anti-unitary operator. Now we see what happens to the Schrödinger equation under this transformation. The Schrödinger equation is given by IH bar times d by dt of ket psi, which is equal to Hamiltonian acting on ket psi. Now the action of the theta operator, the time reversal operator on this equation gives theta IH bar d by dt acting on psi, d by dt of psi is equal to theta h acting on psi. Now since theta is an anti-unitary operator, this would be equal to minus IH bar d by dt times theta psi. So I have written this here over here. So minus IH bar d by dt theta psi is equal to theta h psi. But then again you can insert an identity operator between h and psi, and that identity operator would be theta inverse theta, and therefore this right hand side becomes theta h theta inverse then theta psi, exactly this term. Now theta h theta inverse is the transformed Hamiltonian operator, and we call it h dash, and calling theta psi as the transformed ket psi dash, this equation can be written as minus IH bar d by dt psi dash equals h dash acting on psi dash. And if I call minus t as t dash, then this equation becomes IH bar d by dt dash psi dash equals h dash acting on psi dash. Now this equation looks similar to the original Schrödinger equation, but with a different Hamiltonian h dash. If it so happens that h dash, that is the transformed Hamiltonian, is the same as the original Hamiltonian, then the transformed state in the transformed time obeys exactly same Schrödinger equation as the original state with the original Hamiltonian in the original time parameter. Then we would say that the Schrödinger equation remains unchanged under this transformation. So this happens when the transformed Hamiltonian is the same as the original Hamiltonian, which means h dash, which is theta h theta inverse, is h. Now if you multiply it with theta on the right hand side, one gets theta h is equal to h theta. So if the time reversal operator theta commutes with the Hamiltonian, then the system has a time reversal invariance or time reversal symmetry. Now we consider how the position eigenkets transform under a time reversal operator. We have already required that the position operator remain unchanged under this transformation, the time reversal transformation. That is, theta or theta inverse is equal to r. Now multiplying on the right with theta gives theta r is equal to r theta. That is, r commutes with time reversal operation. Now consider this action of r theta on the position eigenket rho. So r theta acting on rho gives theta r acting on rho. That's because r theta is theta r. Now r acting on ket rho gives back rho times ket rho, because ket rho is the position eigenvector. Now rho is a real number and theta is an anti-unitary operator, but since it is real, it can be taken to the right because rho star is rho. So we get rho times theta acting on rho. That means r acting on theta rho is the same as rho times theta rho. In other words, theta rho is also a position eigenvector with the same eigenvalue rho. Therefore, theta rho should be a multiple of the position eigenget rho. Now, since theta is assumed to be anti-unitary, it shouldn't change the norm of the vector it is acting on, and therefore the multiplication factor should be of unit absolute value. So we can write theta ket rho is equal to a phase factor given by e to the power I omega multiplying the ket rho. Omega is taken to be a real number, so that its absolute value of e to the power I omega is 1. Now we can always choose the convention omega equal to 0, which immediately gives the time reversal operation theta acting on the position eigenket r. It gives back the position eigenket r. That is, the time reversal transformation doesn't change the position eigenvector at all. So this happens under the convention that this phase factor given by e to the power I omega can be taken to be with omega equal to 0. Now we consider the representation of this anti-unitary operator theta in a particular basis. Given an orthonormal basis, an anti-unitary operator theta can always be written as a combination of a unitary operator u and an antilinear operator k. And the action of the antilinear operator is to change a complex number that it acts on to its complex conjugate. Now, suppose we have an orthonormal basis given by kets Ci's. Now, we can always take the anti-unitary operator theta to be u times k, where u is unitary and k acting on the chosen basis vectors leave those vectors unchanged. That is, k acting on Cl is equal to ket Cl, but k acting on a linear combination of those vectors with complex coefficient Cl is given by this equation. That is, k acting on a sum over L Cl, the ket Cl gives sum over L C star L, the complex conjugate of the coefficients multiplying the kets Cl. Now we have to show that this product operator, the uk, is an anti-unitary operator. For that we consider an arbitrary vector written or expanded in terms of the chosen orthonormal basis Cl, and a ket psi, an arbitrary ket psi, can be written as a linear combination given by equation 15.1, and the coefficients are given by the inner product of ZL with the ket psi. And we can do this because the set of basis vectors ZL are orthonormal. Now consider the action of the operator theta defined to be the product of u and k. So we call that vector psi dash, and that would be uk acting on this linear combination. Now k is an antilinear operator, therefore when it acts on a linear combination, it changes all the complex coefficients to its complex conjugates. So the action of k is given here. K acting on this sum gives sum over L, then the complex conjugate of these complex numbers, that is the inner product CL with psi star, times K acting on ZL. But because of this condition 3, the action of K on the chosen orthonormal basis is to leave it unchanged. So we get back CL. Now U is a unitary operator. So action of U on this sum will simply give sum over L, and these coefficients remaining unchanged, then U acting on the ket CL. Now the inner product CL with psi star is the same as the inner product of psi with CL. So we get back sum over L, the inner product of psi with CL, then U acting on the basis vector CL. And you take the corresponding bra, you will get the bra psi dash is simply sum over L, then the complex conjugate of this. That would be exactly same as the inner product of CL with psi. Then the bra CL multiplying the adjoint of U dagger. Now similar to this, we can consider another vector another vector phi, and the action of the time reversal operator on that ket phi. And we will get a similar equation, an equation similar to equation 15.2, and we will get sum over k. Instead of psi we have phi here, so the inner product of phi with ck, then U acting on the basis vector ck. So we have two equations, 15.3 and 15.4, and we can use these two equations to construct the inner product between the transformed states psi dash and phi dash. So this will give so you replace psi dash, the bra psi dash by equation 15.3, and the ket phi dash by equation 15.4, and that will result in sum over KL, then this coefficient, that is the inner product of CL with psi, then this coefficient, inner product of phi with CK, then the bra CL U dagger, then U ZK. So that is given by this term. So that is the matrix element of U dagger U between the orthonormal basis vectors ZL and ZK. But since U is unitary, U dagger U is the identity operator, and this will become the inner product between CL and ZK. Since they are orthonormal, this is simply the Kronecker delta LK. Now the summation over K can be done using this Kronecker delta function. So we will get back sum over L, then the inner product of phi with CL, and then the inner product of CL with psi. But then this can also be written the following way. This is simply phi, then sum over L, ket CL, then bra CL, then ket psi. But this is the resolution of identity, or in other words, this sum is simply the identity operator. And therefore we will get back the inner product between phi and psi, which is the same as the complex conjugate of the inner product between psi and phi. So the inner product of the transformed state psi dash and phi dash is simply the complex conjugate of the inner product of psi with phi, the original state psi with phi, if we write the transformation operator theta as the product of a unitary operator and a complex conjugation antilinear operator k. So this shows that an anti-unitary operator can be represented as a product of a unitary operator and a complex conjugation operator k given an orthonormal basis. Now the action or the particular operators u and k will depend upon the particular orthonormal basis one chooses. And in this course we will be concerned with the orthonormal basis provided by the position eigengets, and so we will deal a bit detail in that basis. So we have already seen here that we can choose the complex conjugation operator k to leave the basis vectors unchanged. So when we choose the position eigenvectors are the basis vectors, we require that k acting on the position eigengets leave them unchanged. That is k r the same as the ket r's. Now k acting on a linear combination of the position eigengets given by integral dr, then the coefficients given by psi r, then the kets r, and that will simply changes the coefficients to their complex conjugates, similar to what we have here in condition 3. K acting on a linear combination changes the coefficients to their complex conjugates and leaves the basis vectors unchanged. And similarly here also the discrete sum has been replaced by integral over dr because r is a continuously varying parameter. In fact 3 parameters here, and therefore the action of k on such a linear combination changes the coefficients psi r to their complex conjugates and leaves r unchanged. Now from equation 14.3 with this choice that omega equal to 0, we see that the time reversal operator acting on the position eigenket leaves it unchanged. So we have already seen that the complex conjugation operator leaves it unchanged, and the product of uk, that is the theta, the time reversal operator, should also leave it unchanged. That is uk acting on r should be r, but k acting on r is r, which means u acting on r should be r. Okay, so the unitary operator u in the position representation, the coordinate representation, can be taken to be simply the identity operator, and we can write theta as k, which is the complex conjugation operator. It changes all the coefficients in a linear combination of position eigenvectors to the complex conjugates and do nothing to the position eigenvectors. Then it immediately follows that the action of theta on an arbitrary ket psi is simply the action of theta on the linear combination dr, then the ket r, and then the inner product of ket r with psi. But inner product of ket r with psi is simply psi of r, and we call it the wave function of the system. So we have a situation similar to this equation, a linear combination of the position eigenvectors and the action of theta on such a linear combination. So that gives psi dash as integral over dr, then psi r will be changed to psi star r, the complex conjugate, and theta acting on r, which does nothing to r, because theta acting on r is the position eigenvalue r itself. Therefore, psi dash is written as integral over dr psi star r, then the position eigenvalue r. Now we can construct the wave function psi dash of r, which is the inner product of position ket r with the transform state psi dash, and which immediately gives back psi star r, because that is the coefficient of the position eigenvalue r in the linear combination. So we see that the action of the time reversal operator on the eigenfunctions in the coordinate representation is to simply change the wave function to its complex conjugate. Now we see that this choice also changes the inner products of the transformed state to the corresponding complex conjugate, and the details is given here, which is similar to this calculation that we have done earlier, and therefore I will not discuss that in detail. Now we consider how the other operators like the momentum and angular momentum changes under the time reversal operation. The momentum we have already discussed, that is theta p theta inverse should be minus p. Now the orbital angular momentum is given by the cross product of the position operator and the momentum operator r cross p, and therefore the theta L theta inverse should be theta r theta inverse cross theta p theta inverse. This is so because we have introduced an identity operator in between r and p, and theta inverse theta is identity. But then theta r theta inverse is r and theta p theta inverse is minus p, and therefore we get minus r cross p and minus L. So under time reversal, the orbital angular momentum changes its sign. So what happens to a general angular momentum operator under time reversal? To see that, we consider the general commutation relation between the angular momentum operators, where if you consider the Cartesian components of angular momentum operators, then J alpha commutator with J beta should be IH bar times epsilon alpha beta gamma times J gamma. For example, the commutator of Jx with Jy is IH bar Jz. Now we can now consider the transformation of this commutator under time reversal, and since time reversal is a symmetry, we expect this commutation relation to remain unchanged. So theta J alpha J beta commutator theta inverse, that should be equal to theta IH bar epsilon alpha beta gamma J gamma times theta inverse. But now if you look at the right hand side, theta IH bar epsilon alpha beta gamma is simply minus IH bar epsilon alpha beta gamma. That's because theta is an anti-unitary operator and theta goes to the right side. Okay. Now similarly, this commutator can be expanded because J alpha commutator with J beta is J alpha J beta minus J beta J alpha, and we can write this to be, that is theta j alpha j beta minus j beta j alpha theta inverse. And if I consider the first term only, this is theta j alpha j beta theta inverse, and in the middle, that is in between j alpha and j beta, I can insert an identity operator, and I will write that as theta inverse theta, and therefore we will get theta j alpha theta inverse and theta j beta theta inverse. Now similarly, the second term gives the second term of this equation, that is this one, and that gives theta j beta theta inverse and then theta j alpha theta inverse, where I have introduced theta inverse theta between j beta and j alpha, and these two together gives back this equation. Okay, so this will give the commutator of theta j alpha theta inverse with theta j beta theta inverse. So the left hand side is given by this and the right hand side is given by this. Okay, so this equation becomes the commutator of theta j alpha theta inverse with theta j beta theta inverse equals minus IH bar epsilon alpha beta gamma theta j gamma theta inverse. Now this equation will be consistent with equation 7.2 if we choose theta j alpha theta inverse to be equal to minus j alpha. Then this would be minus j alpha and this would be minus j beta and this would be minus j gamma. So there will be two minuses here, an additional minus here, and that minus along with this minus cancels out, and these two minuses cancels out here, and we will get j alpha commutator with j beta equal to IH bar epsilon alpha beta gamma j gamma. Okay, so to be consistent, for this equation 17 to be consistent under time reversal, we require that j alpha transforms under time reversal like equation 7.3. They change a sign under the time reversal operation, and so this is analogous to what happens in the case of orbital angular momentum, and using this consistency check we can extend this to all angular momentum operators.